Let's do a couple of examples. In the first one, we have this circuit, 4 amps is flowing. The EMF of the battery is 24 volts, but there's only 20 volts across the terminals of the battery. A and B are the terminals. This is the guts of the battery. EMF source plus internal resistance. So let's figure out what that internal resistance is and the external resistance given the conditions stated, 4 amps and 20 volts. So the little internal resistance, well, R is equal to V over I. It's voltage divided by the current. We know what the current is. We just got to get the voltage. By inspection, you can see it's 4 volts. But remember that the V inside there would be the EMF, but there's a current flow through here, so it's dropped by the voltage across here. So we're given that the entire VAB is 20. So we can just say 24 minus 20 is 4. Over 4 is 1 ohm. So that's the internal resistance. Now, what about the external resistance? The external resistance is its voltage divided by the current, 4. Its voltage is the terminal voltage because it's across the terminals. So it sees the terminal voltage. The external circuit knows nothing about what's going inside here. We already took care of that. So VAB, 20 over 4, 5 ohms. There you go. Now let's do this problem where we have an EMF that we need to discover and an internal resistance that we need to discover. The conditions are that in the normal way current likes to flow, 8.6 volts across the terminals with 3 amps. When it's charging, when you're shoving current the opposite way it wants to go, at 2 amps, there's 10.1 volts across the terminals. Looks like 2 equations, right? Let's do it. VAB for the first one is 8.6 volts. It consists of the EMF, but dropped minus to plus, and then there's going to be plus to minus. There's going to be a drop across here. So minus 3 times 3 amps times the resistance, whatever it is, call it R, equals 8.6. Going the other way, we have VAB is 10.1. It consists of plus to minus, plus to minus. So if you go across this way, there's a rise and another rise. So we have the EMF plus 2 times this resistance equals 10.1. All right, so we can basically take this one and subtract this one. That's what I'm going to do. And so these go away. 2R minus negative 3 is 5 equals 5R equals 1.5. R is 0.3 ohms. Now we can just stick that back in for this one. EMF is 10.1 minus 2R gives us 9.5 volts. And so there's our answer. In this example, let's find the current in the circuit, and then let's also find the voltage of A with respect to B, and also VAC, voltage of A with respect to C. And then let's graph the potentials. Well, current is EMF over R. Well, you can think of the total contribution of the EMFs. We have 2 batteries here. They're kind of fighting each other, right? By inspection, you can probably see that the 16 volt wins because this is only 8 volts, which is positioned the other way. So 16 minus 8, that's the EMF, and the resistance is 1.6 plus 5 plus 1.4 plus 9. That gives us 0.47 amps, and it's going counterclockwise. Pretty easy to see that. Now VAB, the voltage of A from the point of view of B, that's what we're looking at. So B is over here looking at A and saying, from my point of view, I see a rise of 16, but then there's a drop. If it wasn't for this drop, I would see A at 16 volts compared from my point of view, because it's higher on this side than this side. So A is at a higher potential, but dropped by this amount. So VAB is EMF minus IR, 16 minus 0.47 times 1.6. So it drops to 15.2 volts. A is 15.2 volts higher than B. How about VAC? Well, from the point of view of C, let's see, we got current flowing this way. So this is plus to minus. There's a drop from here to here, and then a rise, and then another drop. So we got another little drop across this one from the point of view of C, looking at A. So it's VAB minus 0.47 times 9, drop across this one, which is 11 volts. Now we could go the other way. We could go this way and do the same thing. All right, so there we have, we're over at C. We know we have current flowing like this, so it's plus to minus, and plus over here to minus, because of the way the current's flowing. So those are both rises in going from C to A. And there's also this rise. There's a, from C, looking this way, there's a 8-volt rise, and then there's another rise across here and a rise across here. So those are all positive values. So it's 0.47 times 5 and 1.4, and then an additional 8. So that should also give you 11. Now let's graph it. V, let's start at B. So I'm going to start at B and go counterclockwise. And so I'm going to put the first 16-volt EMF. This is a rise. So across this element, it rises from our reference value 0 at B up to 16. Then the next thing it encounters is the 1.6 ohm resistor and going to A. That drops it a little bit. Now there's no drop along the conductors, so that's what this is. On the conductor itself, no drop. Across the element, it drops to 15.2. Then it continues on to the 5 ohm resistor, and that drops it some more. More so than the 1.6. We could calculate it, but that's not so important right now. Next thing it encounters is the 1.4 ohm, and that drops it a little more. And then it encounters the 8 volt. You're going from plus to minus, so that's a drop, and it's a specific drop of 8 volts. So across this little region, 8-volt drop across that battery. And finally, we're at C now. We're going to go back to B, the original the starting point, which of course has to be the same potential that we started with. So across the 9 volt, and 9 times 0.47 should give us this magnitude, and we're back at B once again. So we've completed the entire circuit path and seen how the potential rises and then drops the exact amount that it rises. And so the energy per charge is the same at both locations, B and B, and makes the noted transitions along the way. In this example, we will look at the voltage VAD. What is VAD? Voltage of A with respect to D. We'll go in both directions, look at it from 2 different points of view, and also what's the terminal voltage of the 4-volt battery. That's across this thing. All right, so VAD. What's VAD? Well, we have to find the current in the circuit, because then we can get the voltages properly. So we need to know the direction and the size. So that's easy. I is the sum of the EMFs over the sum of the R's. The EMFs, consider them algebraically. We see the 8-volt trying to go clockwise, the 4-volt trying to go counterclockwise. The 8-volt wins. So we have 8 minus 4 over 0.5 plus 8 plus 6 plus 0.5 plus 9, giving us 0.167 amps. And that's clockwise. That's the direction the current's flowing. So let's do VAD. Let's go clockwise. The voltage of A from the point of view of D. So when we go clockwise, since we're actually the current's flowing this way, we have plus over here to minus. Plus to minus. And here's plus to minus. Plus to minus. From the point of view of D, and we're moving around this way, as D looks back, it sees a rise across here, and a rise here, and a rise here, and a rise here. So that directs us as to the sign. 0.167 current times the 6 and the 0.5 and the 9. And added to that is going to be the 4, giving us 6.59 volts. Let's do it again the other way around. Let's go the voltage of A from the point of view of D going counterclockwise, going this way. Well, the current's going the other way. So since the current's going across like this, it's plus to minus. So when we're at looking at A from D, we got plus to minus. There's a drop going this way, and it's a drop going this way. But this is a rise, minus to plus. That's a rise. So we have the negative, the drops, 0.167, 8, and the 0.5. And then we have to add 8. And that gives us, hopefully, the same thing, and indeed it does. Now, the voltage across the 4 volt, well, let's see. Current's flowing like this. This is plus to minus and plus to minus. It's driving current in a way such that the battery is charging. So it causes a rise in the potential across the whole battery. So we're going to have the 0.167 times 0.5. That rise inside plus the additional 4. So plus 4 plus whatever that IR is. Gives us 4.1 volts for VBC. And now for fun, let's add another battery to the circuit. It's a 10.3 volt battery over on the right with a 0.5 ohm internal resistance. And let's get VBC, or the terminal voltage of the 4 volt battery. Well, this just changes the situation a little bit. Now that we have 10.3 oriented the way it is, it's adding to the 4 to overcome the 8. So let's get the new current. It's a counterclockwise current now. Sum of the EMFs over sum of R. 10.3 plus the 4 minus the 8 over all the resistances. No, thinking like resisti. No, that doesn't work. Resistances, okay. Gives us 0.257 amps counterclockwise. So reverse the direction of current. Now this battery is flowing current the way it likes to do it. And so this, there's a rise across here, and then it's a plus to minus. So there's going to be a drop across this one. So it's going to change things. So we have VBC now is the rise of 4 minus the I times R. So that's 4 minus IR is 3.87 volts. It's acting like a normal battery with a voltage drop internally.